Hi again. This is Myint. I'm a professor in the School of Geographical Sciences and Urban Planning. I'm going to continue my remote sensing lecture. This is part 2 of remote sensing. So let's start with the pixel size. Pixel size is also related to scale. Right? So map scale or air photo scale, whatever you're thinking, it is the same. So the pixel size on the other end, left side of the image shows the small ground resolution or cell size. The one in the middle is the medium pixel size. The one on the right end is the large ground resolution. So in general, the smaller the pixel size, the clearer the picture, the higher the level of details. And so let's say if you use a camera mounted to a low-flying aircraft and take the picture, then you can see things a lot clearer than the same camera that you mounted to a high-flying aircraft and take the picture. But that particular picture taken by an aircraft at a high altitude will cover larger areas, but the lesser details. Right? So then the same camera that you use and then mounted to a spacecraft, your coverage will be a lot bigger. You get a larger coverage, but lesser details in general. So if you think about this as a pixel size, the one at the bottom, low-flying aircraft produce smallest pixel size. The one from the satellite image, the one that you take your picture from the satellite, will have the biggest pixel size. That coverage is also very large, but lesser details, right? Okay, photogrammetric scale. So let's start with map scale. This is normally interpreted as the ratio of a map distance to the corresponding ground distance. You measure one particular feature or intersection of two roads, let's say Rural and McClintock to Rural and Apache. On your map, you measure it, it is 1 centimeter. You check it on the ground, which is like 5,000 centimeters on the ground. Then your map scale is 1:5,000, right? I'm just giving you as an example. It may not be true. Photogrammetric scale, the same thing. Photo distance divided by ground distance. That is your photo scale. Distance on a photo divided by the distance, the corresponding distance on the ground. Same thing. So due to the nature of map projections, the map scale is not influenced by terrain variation, the height and distortion. An aerial photo, however, is a perspective projection. Its scale varies with the variations in terrain elevation. So you can see this diagram in terms of a map scale. So A prime, B prime at the bottom divided by big AB on the ground. And the scale of a photo is small ab divided by big AB, that small ab that you measure on the photo, and then the same distance on the ground. So this is just an example. I'm giving you fine resolution air photo. It could be about 3 meters, and this is 6 meters, and this is 12 meters, this is 24 meters, this is 48 meters, right? So this is 96 meters. So what I'm trying to demonstrate is that when you change the pixel size, your image is showing basically lesser details. But I'm giving some other example. This is like 1 meter resolution. This is like 2.5 meter resolution. And this is like 3.5 or 5 meters air photo. And this is one satellite image, which is 5-meter resolution. And this is a one band grayscale of that particular satellite image. And this is Landsat 30-meter resolution. Oh, that one was Indian remote sensing satellite image. This is Landsat 30-meter resolution. This is another satellite image at 70 meters resolution. Right, so this one, another example, this is a little coarser resolution. When you have a finer resolution, you can see things better. This is Washington, D.C. And I'm going to give you some example of how we can identify land use land cover maps. Right, so if you take a look at it from the left side, level 1, you identify those classes from your satellite image. One is urban, another one is agricultural, another one is rangeland, another one is forest, then water, wetland, barren land, tundra, and then perennial snow or ice. When you go for the level 2 using a different satellite image, you'll be able to identify higher level of details. For example, in the case of level 1, you can identify urban areas. But in the case of level 2, you'll be able to identify residential, commercial, industrial, transportation, industrial and commercial, mixed urban, and other built-up lands. So you can identify a lot higher level of details. So you can imagine that the satellite image that you use to identify level 2 classes basically has a smaller pixel size. Remember, the smaller the pixel size, the higher the level of details, right? So level 1 does not have the detailed land use land cover types, but level 2 has a lot higher level of details. That means your satellite image pixel size is a lot smaller. Or in terms of scale, it is a large scale satellite image, large scale satellite image, or large scale air photo, whatever you call, but it has smaller pixel size. So let me give you another example. That level 1 satellite, you can identify one particular type for urban area, that is urban or built-up class. But for level 2, smaller pixel size satellite image, you're able to identify residential, commercial, industrial, transportation, industrial and commercial, and mixed urban, and so on. Then when you go for even a smaller pixel size or a lot larger scale air photo, a small pixel size satellite image, even for residential area, you'll be able to identify single family houses, multiple family houses, group quarters, residential hotels, mobile home and transient lodgings, and so on. You can even identify a lot more classes within that one particular class because you have a larger scale air photo or larger scale satellite image or finer resolution satellite image that you have. That's why you're able to identify, you can see things a lot better, and you're able to identify higher level of details. So why remote sensing? Why do we need remote sensing? Why do we use remote sensing? That's a big question. The first answer is larger areas can be imaged quickly and repeatedly. So basically, if you need to do a particular land use land cover map, a forest type maps, or agriculture crop type maps for the entire state of Florida, something, then you can take a picture over the entire Florida with bigger pixel size or coarser resolution satellite data and do whatever you need to do, and then you can produce it on January 21st or 23rd February or August 15th, and then whichever time fits better for you, you can take it, or you can take every year or every month or every 8 days or 16 days. That is why we use remote sensing. We can get any time we like. We can get a larger area, or you can take it again and again. If you're using your air photo, your aircraft to take picture whenever you need, take it, interpret it, convert it to a map or information, whatever information you need to extract. Right, so that's why we need remote sensing. Images can be acquired with a spatial resolution that matches the degree of spatial detail. So basically, do you want a 50 centimeter resolution satellite image, or do you want a 1 kilometer pixel size for larger areas? For example, if you want to do a regional level climate analysis or climate simulation, you would want to use bigger pixel size. For example, 500 meters or 1 kilometer resolution satellite data would be a good fit to achieve whatever the objective that you would like to achieve for your regional climate modeling. But if you would like to do a local study of boundary layer study of urban climate or urban heat island at a micro level detailed analysis of those houses and driveways and sidewalks and swimming pools and trees locations and grass and shrubs and open soil, all of them, how they influence air temperatures and surface temperatures and urban heat island, then you might want to go for 1 meter resolution satellite data. Whatever you need, you can take it and then go for your project to achieve whatever you would like to achieve. So remote sensing images eliminate the problem of surface access that often hamper ground surveys. So if it is very dense evergreen forest or mangroves that you cannot go through that forest, or a particular situation doesn't let you go, for example, any disaster event for a particular hurricane or thunderstorm or typhoons or earthquake or anything that won't let you go and take the survey or do proper management plans, you will need a remote sensing. Any disaster event, it could be tsunami events, it could be cyclone event, it could be hurricanes, anything that will basically hamper your ground service. You can take the satellite image, make a better management plan. You can do the damage assessment, which parts are the best network or system and routing networks to better manage this disaster event or disaster mitigation or disaster management plan that you can do with the use of a satellite image. Right? In some cases, even it is not a disaster event, it is not earthquake, it is not tornado, it is not cyclone, it is not tsunami, you simply cannot go and do the ground measurement in many, many cases. Very, very dense evergreen forest or very, very dense bamboo forest, very, very dense mangroves, those kinds of situation, wetland, all these things, you can take a picture and do the analysis and come up with better management plan and go for your assessment and monitoring. And then images provide a perspective that is lacking for ground surveys. If you just stand in the middle of a forest, then you don't know exactly how these things are arranged in space. Right, so you have agriculture around that forest, or there is a secondary forest next to the forest, or forest plantation is on the right side, or southeast direction has a big water body, or there is a river next to it, or there is some kind of urban areas that you need to take care of water competition between urban areas and agricultural area, or carbon release from urban areas, or carbon release from net primary productivity from forest areas. You make a better management plan considering many different factors, many different areas, interdisciplinary kind of decision making, a transdisciplinary work that you need to think together in many different areas or many different natural resources or man-made features and make a proper management plan for sustainable development. You cannot just stand there and then take a look at it for a smaller area and come up with a bigger picture and bigger management plan. That's not possible. You need a remote sensing. And image interpretation is faster and less expensive than conducting a ground survey, right? So if you would like to have a forest survey for the entire state of Michigan, for example, and then you will need to employ hundreds of thousands of survey crews and forest rangers and forest officers and inventory experts and inventory crews and take every measurements on the ground. That's not possible. You can take some training samples, some kind of sampling scheme, and then take the inventory properly, systematically, which could be 1,000 meters apart or 2-3 kilometers apart for whatever the sampling system, stratified random sampling or systematic sampling approach, and using satellite image link with whatever you collect on the ground, and then come up with the deforestation rate, or reforestation rate, or forestation rate, carbon release rates, and wildfire events, and so on, based on the remote sensing. And image provide an objective permanent data set that may be interpreted for a wide range of land use land cover. So you can identify one land use land cover map that can be used for agricultural management, that can be used for land use management, that can be used for food security, that can be used for water management between urban areas and agricultural areas around the city, better management plan for groundwater contamination due to insecticides and pesticides used from agricultural area, and those from stormwater pollution that is basically carried away from urban features. That kind of thing that you would need a permanent land use land cover type, you can use for many different applications or come up with better management plans. Right, so some example applications that I'm showing this one before, but this one is a little bit finer resolution. And then this is wildfire event that you can see in the satellite image. This is, I believe, is San Diego, and then you can extract the man-made features, impervious surfaces. You can also extract trees and grass and shrubs separately, and then make decisions or do whatever the analysis you need to do. The one on the left, top left corner, is one fine resolution satellite image. At the bottom, I put a land use land cover map that I prepared. And then we can also use nighttime temperature and daytime temperature during the summer and winter, and do the analysis how urban heat island influence, how land use land cover types influence urban heat island, how they alter those surface temperature and things like that. You can check. This is the fine resolution satellite data. This is the output map that you can see all the details, individual houses, roads, trees and grass and shrubs and water and swimming pool, all separately that we identify so that we can do all kinds of detailed analysis. So this is another example, the global night lights. You can see this kind of analysis. We can link with the night lights and the population pressure, population density, population counts, economy, per capita income, household income, and some kind of human development index, or unemployment rate or poverty rate, and education level, whatever you need to you would like to explore. You might be able to link with all these night lights and then socioeconomic status of different countries and different cities and so on. So here is global net primary productivity, which is basically the carbon sequestration that the trees basically absorb the carbon and release oxygen into the air, and that amount of carbon that they kept during their food production minus the amount of carbon that they release during the respiration period, that difference is basically the amount of carbon trees basically capture, which is carbon sequestration. You can see for the whole world. And this is global land surface temperature. You can see which part of the world is warmer. And then you can see global carbon monoxide. This is global fire, where the wildfires occur across the globe. And that is the end of my remote sensing part 2. Thank you.